Okay, so you put on a VR headset and boom, you're somewhere else. It feels real, right? But how does that even happen? How do we go from lines of code to a world that can actually trick your brain? Well, that's exactly what we're going to dive into. We're pulling back the curtain on how these incredible virtual worlds are built from the ground up.
All right, here's the plan. We'll start with the big picture, the system's architecture. Then we'll get into the fun stuff, actually building the world and all the objects in it. After that, we'll see how they make it all look real with lighting and textures. Then we'll talk about making it feel real with haptics. And finally, we'll look at the magic that keeps it all running without crashing.
Okay, let's kick things off with the foundation. You gotta have a blueprint before you start building, and it's no different for a virtual world.
So take a look at this. It's actually pretty straightforward when you break it down. Right in the middle, you've got the VR engine. That's the brains of the whole operation, crunching all the numbers. It's constantly talking to the I/O devices. Think of those as the system's senses. Your headset, your controllers, anything that gives you feedback. And right there, at the very center of it all, that's you, the user. The entire system revolves around your experience.
All right, we've got the blueprint. Now, how do we actually build this stuff inside the world? The walls, the tables, the characters, where does it all come from?
And check this out, because this is super important. Building something for VR isn't just about sculpting a 3D shape. It's way more than that. You have to define its geometry, sure, but you also have to give it physics, like how does it fall? You have to define its behavior, what does it do? All these pieces get fed into what's called an authoring tool, which then spits out the final simulation that you can actually interact with.
So how do you actually make these objects? Well, you've got options. If you're a hardcore programmer, you can code them from scratch using toolkits like OpenGL. It's tough, but you get total control. Or you could use a CAD program, like AutoCAD, which is what a lot of architects and designers use. But the really cool method, you can use a 3D scanner to just zap a real-world object and pull a perfect digital copy right into your virtual world. Pretty neat, huh? Okay, so you've got your 3D model, but at this point, it's basically just a wireframe skeleton. It looks like a cage, right? There's no substance to it. That's where shading comes in. Shading is the magic step that fills in the surfaces and makes that wireframe actually look like a solid object with volume and depth.
And this picture says it all. Look at the teapot on the left. That's flat shading. You can literally see every single flat polygon it's made of. It looks like a low-res video game from the 90s. But then look at the one on the right. That's Phong shading. It's smooth, it's shiny, it actually looks like a real teapot. It's the same model, just a different, smarter way of handling light.
Okay, our objects look solid. That's a huge step. But a world full of smooth, single-colored objects is still pretty boring. Now we need to paint them and light the scene properly. This is all about rendering and illumination.
Texture mapping is probably one of the cleverest tricks in all of 3D graphics. The best way to think about it is like digital gift wrap. You have a plain 3D box, and you have a flat 2D picture of a brick pattern. Texture mapping is literally just wrapping that picture around the box. And just like that, your plain box is now a brick wall.
And this is how it works under the hood. You start with the texture space. That's your flat 2D image. The system then does some pretty complex math to project that image onto the object surface. Once that's done, the now textured object is ready to be shown in screen space, which is, well, what you see on your screen. It's a 3-step process to get that detail on there.
And here is the payoff. Wow, look at that. The wood grain on the floor, the rough texture on the walls, even the art on the wall. Every bit of that detail is just a 2D image wrapped onto a simple shape. This is what turns a boring, sterile-looking room into a space that feels real, a place that feels lived in.
But textures are only half the battle. You need good lighting. The scene on the left, the lighting is fine, I guess, but the shadows are super harsh and dark. It looks fake. Now, the scene on the right uses a technique called radiosity. It calculates how light bounces off of surfaces. See how the shadows are softer? And notice how the red floor kind of bleeds a little bit of red light onto the white walls? That's what happens in real life. It's these little details that sell the illusion.
So the world looks real. That's awesome. But what happens when you try to touch something? To really be immersed, you have to be able to feel the world, and that's where haptics comes in.
This is the process for faking the sense of touch. First, the system has to figure out if you've even touched anything. That's called collision detection. As soon as it detects a touch, it calculates how much force you should be feeling. Is it a hard wall or a soft cushion? Then it sends that information to your controller or your gloves, which generate a vibration or resistance, and you feel it.
Yeah, to put it simply, collision detection is what keeps you from being a ghost in the machine. It's the system's way of knowing that your hand has hit a virtual wall instead of just passing right through it. It's absolutely fundamental for any kind of physical interaction.
But here's the problem. Checking if two really complex objects are touching polygon by polygon takes a ton of computer power. It's just too slow. So developers use a clever cheat. They put a simple, invisible bounding box around every object. Instead of checking the complex shapes, the computer just checks if the simple boxes are touching. It's way, way faster.
But that little shortcut creates a weird problem. Think about something moving really fast, like a bullet. In one frame, one snapshot in time, the bullet is on this side of the wall. In the very next frame, it's already on the other side. It moved so fast that it completely skipped through the wall between frames. The system never saw the two bounding boxes overlap, so as far as it's concerned, the collision never happened. It's called tunneling, and it's a huge challenge for developers.
Okay, so we've got this amazing, beautiful, interactive world. But all these calculations, the shading, the lighting, the physics, they're incredibly demanding. So how on earth do you get all of this to run in real time without turning into a slideshow? The answer is optimization.
And one of the most important optimization tricks is called level of detail, or LOD. And the logic is just pure common sense. Think about it. If you're looking at a tree way off in the distance, you can't see every individual leaf, right? So why waste computer power drawing every single leaf? LOD is just the system being smart about it. It uses super detailed models for things right in front of you and much simpler, blockier models for things far away.
And just look at the numbers here. The sphere on top is made of almost 8,200 triangles. The one on the bottom, just 537. From a distance, you probably can't even tell the difference, but the simple one renders nearly 5 times faster. That's a gigantic performance boost, and it's what makes huge, open virtual worlds even possible.
This graph really drives the point home. On the left, without LOD, look at those huge spikes in frame time. Each one of those spikes is a moment where the game stutters or lags. In VR, that's not just annoying, it can literally make you feel sick. But on the right, with LOD turned on, the performance is so much smoother and more stable. This isn't just a nice feature to have, it is absolutely essential for a good VR experience.
So all this technology is all pushing towards one thing, perfect realism. But as we get closer and closer, especially with human characters, we hit this really weird, really fascinating problem called the uncanny valley. What this graph shows is that as a character gets more realistic, we like it up to a point. Then, when it's almost perfect but just a little bit off, our brains just reject it. It looks creepy. It feels wrong. It's a strange trap where something that's less realistic can actually feel more appealing. Which leaves us with a really big question for the future. As our tech gets better and better, are we ever going to be able to completely cross that valley? Can we create virtual people that are so perfect our brains finally accept them? Or will we always, on some deep level, be able to spot the fake? Something to think about. Thanks so much for watching.